So thank you everybody for joining the Spring 2021 Forum. We are really happy to have Dr. McKenzie West here with us today. But before we get to the actual presentation, let me remind you of a few housekeeping items. Well, as you can hear just now, the presentation is being recorded so that we can share this work with more folks on campus. And as a reminder, during the presentation, if you can check that your microphone is muted, that would be greatly appreciated just to minimize any extraneous noise and distraction. We obviously welcome questions. So at the end of the presentation, you can unmute yourself and ask a question, or I think if you prefer to drop your question in the chat box, that would be acceptable, of course, as well. And I will be monitoring the chat box just in case Dr. West is busy answering other questions. Okay, so with that, I would formally introduce our speaker today, Dr. McKenzie West. She is an assistant professor of mathematics and teaches in the data science master's program. McKenzie earned her PhD from Emory University and her bachelor's of arts degree from St. Olaf College. Before arriving in Eau Claire, she held visiting positions at Reed College and Kalamazoo College. Her research is in the field of number theory, and she enjoys the algorithmic study of solutions to polynomial equations. So thank you, McKenzie. The platform is yours.
All right. Excellent. Thank you for the introduction, Catherine, and the invitation to speak today. So the topic I'm going to talk about is cryptography, which is maybe one of the most popular applications currently for number theory. So I don't directly do cryptography research, but in theory, the research that I do does apply to cryptography. So why not talk about it today? So to get started, let's first talk about what I'm talking about. What is cryptography? So cryptography is the practice of making your internet communication or your computer communication secret. Well, not just computer communication, any communication secret and away from someone that you don't want to hear about it. So we have the encryption, which is the process of changing ordinary text to unintelligible text. And then decryption would be the reverse of that process. So in general, we want to think of good ways to encrypt and decrypt so that our communications are secure. In general, in sort of computer science context, everywhere I've ever seen anyone talk about cryptography, Alice and Bob are the two communicators, and Eve is the one trying to interrupt or intercept or anything of the above of the communication. So I will continue to talk about them today. But I will do my best not to use any pronouns for either of them because, I mean, whatever, we all send messages. So let's do it. So really what we need is we need good keys to lock up our information. So how are we going to generate good keys and good ciphers? One cipher that you may have heard about before is that of the Caesar cipher, which sort of just shifts the alphabet. So for example, you can shift it by 2 and change the word hello to FCJJM, just by sort of going backwards every 2 letters. And then to decrypt FCJJM, you would just move all of the letters forward. This is called the Caesar cipher, based off of Caesar himself. And it's a very old cipher. This is not what computers use. And I'll point out that in this case, they are using the same key. So they both had to know the value of K going into the conversation. So the name for this type of cryptography would be called symmetric key cryptography. So Alice and Bob, they were sending their messages by shifting the letters. And they both had that same K value to encrypt and decrypt. And so there's a big disadvantage of this, and that disadvantage is the fact that they had to know this key beforehand. When we're communicating and trying to send our order into Amazon, we haven't discussed with Amazon beforehand before entering the internet communication about a secret key for us to use. Here would be another example of secret key cryptography, where your keys are kind of kept secret between the two users, the Alice and Bob. So Enigma machine would be another example. And again, the main idea is that Alice and Bob, they share a private key between themselves that they aren't going to share with anyone else, and we're going to keep totally secret. Now, as I said, that's not what we do when we talk to Amazon, because that's not how it works. We don't like go into this having already spoken to Amazon outside of the internet and made an agreement. And we can't just send a key over the internet, because then someone could just grab it out from us. Eve could just be standing there waiting for it to be sent. So in comes the concept of public key cryptography. So this would be in 1976. Diffie and Hellman proposed a public key or asymmetric key cryptography. So Diffie and Hellman are going to be two names if you ever start looking into cryptography that you will see a lot. So what happens is that Bob, the person receiving the message, generates two keys and creates one public and holds the other two themselves. And Alice then takes that public key to hide their own message that they're going to send to Bob. And Bob's going to be able to use his private key to sort of undo the hiding that Alice did using the public key. And the undoing is only possible with that private key that Bob has held on to. One quick historical note here, I guess, is that in fact, this notion was actually discovered earlier, as far as we're aware, in 1970 at Government Communication Headquarters, which was classified until the 90s, the late 90s. So there are public and private entities both working to create this cryptography and these methods, and the government is holding some of it secret, as we might expect. I mean, that feels natural. Anyway, so to continue on, I have a few notes about complexity. So one thing I will say is that public key cryptography is computationally expensive. That's because our keys need to be exceptionally massive numbers so that they can really hide any of the information, and ultimately you're producing large numbers that you're sending. And I guess the undoing is computationally expensive, but sort of the breaking in and trying to attempt the undoing if you don't know the key, in theory, is so expensive that it's impossible. In theory. Yeah. So that last note is the important one. So mathematically, we're assuming that the operations we're using to hide the message is easy to do, but hard to undo. So if you have the public key, you know how the message was created, but you don't know how to uncreate the message to decrypt. All right, so let's continue. Give you a quick motivational example about that last note about complexity. So just think for a second. I've listed two sort of problems you might find on a math test. One is multiply these two numbers, a 4-digit and a 3-digit, or factor this number that has, 7 digits. So if you think about which one of these sounds like a simpler problem, I would say that the first one definitely does. And maybe given the way that I've stated them, you might guess that the second answer is that the factorization is given by the first one. Anyway, we'll ignore that fact and we'll assume that it's much easier to multiply than it is to factor. And that's going to be our key for our cryptography that we're going to discuss, at least today. So I have a lot of words in this box right here. But generally what they say is that Bob's two keys are those two numbers that we were multiplying together. And well, the two numbers are the secret key. The public key is their product. And so in theory, it's going to be hard for someone trying to break in to factor that product. So something like this is sort of how the most common algorithm works. So one of the most common algorithms on the internet that you'll see is this RSA algorithm invented in '78. And it uses a whole lot of number theory in it. So RSA, after Revest, Shamir, and Edelman, they published the first public key crypto system. So that idea that Bob is creating two keys and sharing one of them. And it relies on this fact from the last slide, that it's easy to multiply but hard to factor. And in that last point there, I'll show you how to figure out which encryption algorithm the website you're looking at uses. But what you'll end up finding is that most of them that you run across are using some version of RSA. And again, let's add another historical note. The equivalent system was discovered in 1973, again at the government communication headquarters. So I guess these are natural algorithms to come up with given the information, given the mathematics that we know. And I guess maybe they're not even that new of algorithms. What, 1973 was almost 50 years ago? So there are certainly modern approaches to this, but and various avenues people are trying to go to get better encryption systems. Anyway, let me talk about this problem called the discrete log problem. It's going to expand on the idea of how difficult it is to multiply integers and give us an even harder problem, which is taking the logarithm of integers. So if we have two integers a and b, for which a to the k equals b, so if you multiply a by itself, however many times, k times, you get b, and you don't know what k is, it's actually really hard to figure out what k is. It's really hard to figure out the logarithm of b mod a, especially when these numbers are huge. So like if the numbers are small, okay, fine, plug it into a calculator, it's not hard. If the numbers are huge, this is very difficult. So let's talk real quick about the number system we're using, because actually computers, they don't have infinite space for infinitely sized numbers. We actually use this thing called modular arithmetic to cut off numbers at some point along the line. So real quick, this first line, the division algorithm. So think back to, what was it? I think I learned this in 3rd grade, where if you take a number and you divide by another one using sort of long division, you'll get some remainder at the end. So either you'll get 0, which would be great, or you'll get some remainder. And that's sort of what we're thinking about here. So I've taken, what have I done? N, the number n, and I've divided it by the number a, and r is our remainder. So we're going to say two integers are going to be equivalent. Oh, goodness. I'm going wild with my notation. Let me grab my pen out so that I can do this better. N and A have swapped meanings sort of between this first and second one. So choose what you like. I guess maybe I'd swap the first N and the first A as opposed to the second N and second A. But let's see if I can get my eraser out. There we go. So I swap that N and the A there just for the sake of our brains. But the point is, we're going to say two numbers are equivalent, mod n, if they have the same remainder. Here's my laser pointer. If they have the same remainder when you divide by n. So in the division algorithm, I'm thinking a divided by n instead of n over a. Anyway, what's the point? So for example, you've done this before in your life. I promise you have. When you're figuring out times on a clock, if it's 8 p.m. and you're trying to figure out, okay, in 7 hours, what time will it be? You add 7 to 8, that's 15. But you're not looking at 15 o'clock. 7 hours after 8 p.m. is 3 o'clock. And how do you know that? It's because that 15, you kind of see, okay, how far did 15 go past 12? It went 3 past 12, so therefore it'll be 3 a.m. in 7 hours. And what you're doing there is you're taking mod 12. 15 is congruent to 3 mod 12 because that's how far away they're both the same amount away from 12. Maybe just to clear this up a little bit more, right? I have that same example right here. 8 plus 7 is 3 mod 12, which is very nice. And you can even do a similar thing, multiplication. If you do 8 hours 7 times, if you start at midnight, you'll get to 8 on a future day. If you do 8 7 times. AM or PM, we're kind of ignoring that for the moment. Yeah, so the point is that you kind of consider all of the remainders when you divide by n, and what this is going to allow us to do, the reason that we do this is, again, that a computer can't take an infinitely long number. It has a limit, sort of a memory limit almost, is how we want to think about it. And so if we add two big numbers together, we kind of want to just cut them off at some point and sort of loop back around to the beginning. And that's what we're going to do when we're adding our large numbers. Now, in the computer case, n is going to be exceptionally massive. A and B are going to be exceptionally massive. So the problems get difficult, I guess. There's also a question of, can we do dividing mod n, and what does it mean to divide? Well, dividing only works if you have no common factors with that modulus. So in the 12 case, we can divide by 7 because there's something that we multiply to get 1, but if we were multiplying by 8, there's no b value, there's no number we could use for b that would get us to be 1 more than a multiple of 12. And that is because 8 and 12 share a common factor of 4. I mean, they also share a common factor of 2. They share anything other than 1 or negative 1. Do we want to count negatives? We can fight over it. But so division gets a little bit tricky, but I will point out this bullet point here is that, in fact, it is still easy to compute this value using this thing called the Euclidean algorithm, which is very easy to implement. Actually, one of my students implemented it for a discussion post last week, and it took just a couple lines to do. So very easy to compute, even these inverses. So division actually is also, let's put it in quotes, easy to do mod n. So the last thing, logarithms. Now these, again, are going to be harder to do mod n. So if we have a to some power k being b, it's very difficult to figure out what that k is unless you already know what k is. So for example, here I have a good question, and of course I thought in my head I was going to remember what the answer was, but I don't remember what the answer is. I believe, if I had to guess, K is, I think 100. I think 100 in this example. And how would I figure this out? Like, I think what I would actually do is brute force. I'd say, what is 3 to the 1? What is 3 to the 2? 3 to 3, etc. until I figured out, until I got to the point where I got 2 sort of as the remainder when I divided by 101. So, I mean, there's not much better of a way to do this than with brute force. And that's what makes this problem hard, and that's what makes this a good tool for cryptography. So we make N exceptionally massive, A massive, B massive, K massive. It's going to be hard to figure out what K is in some reasonably amount of computation time. That won't take, I don't know, billions of years. Sort of, it's impressive how quickly the time adds up with these problems. So let me just remind you of a few things of what we're going to take away from this section of the talk is that multiplication in addition are easy, raising things to exponents are easy, computing greatest common denominators is easy, inverting is easy, meaning division meaning inverting, and the logarithm is hard. This is what we're going to take away. So what we're going to be doing when we're encrypting things is we're going to be using this first to sort of hide our message, to undo the hiding, to decrypt. And this is what's going to keep Eve from grabbing our message and figuring out what it is themselves. So from finding our credit card number within the message we've hidden. So let me just talk about, roughly speaking, what a crypto system would look like using this difficulty of the logarithm. So what Bob is going to do is going to choose a prime number. It's going to be a really big prime number, and some integer a that doesn't have that prime number as a factor. Bob is then going to choose a secret number k that's going to be that exponent. So Bob computes b, a, or picks a, p, and k, and then computes b. B is a to the k. And then Bob is willingly and openly sharing a, b, and p, and keeping that k, that exponent, secret. So remember, what I was just saying is that k is really hard to figure out if you don't know what it is already, even if you know all of the other numbers in this equation. So that's what we're kind of banking on here in this encryption. And this is what RSA is doing. So then Alice wants to send Bob this secret number M. So imagine credit card number here, for example. What Alice is going to do is compute these two numbers, A to some Y, and M times B to some Y, where Y is some secret number that Alice has chosen. Again, Alice is going to keep Y private, right? It's going to be hard to undo that Y exponent business there. So it's going to be hard for Alice to figure out what M is, even though we slid M into the C value. So then Alice goes ahead and sends Bob the two numbers that they computed and keeps Y private to themselves. So then the goal is that Bob uses their knowledge of A, B, and K to then be able to undo the multiplication that Alice has done and figure out exactly what M is. So how is that going to happen? So here's actually the formulas that we can use. So we notice first off that, okay, B, we computed. Bob computed B themselves, excuse me. B was A to the K. So this is kind of an equality here, an equivalence. And then you can use your laws of exponents to swap around the order. You can put the y on the inside, the k on the outside. And that's exactly the number C1 that Alice sent to Bob, just to the kth power. So b to the y is C1 to the kth power. So Bob knows exactly what b to the y is. So in our second equation here, where C2 was the other number Alice sent, then we can actually figure out exactly what C2 is, because Bob has now figured out what b to the y is, even though Bob doesn't know what y is. But they do know what the entire b to the y. And so they can actually divide that out and solve for n. So in fact, Bob is able to figure that value out quite easily. This is literally 2 relatively small computations that Bob needs to do to figure out exactly what the message Alice sent was. So I'll pause there for a second, maybe to let you absorb that, what's going on. Whether or not you're happy about the math I've written, specifically, I'll just remind you that Bob and Alice have this sort of secret to themselves, but are able to share a message nonetheless, using public information. Thank you, PowerPoint, for introducing this lovely animation. But I'll point out, so RSA encryption, as I said, this is most commonly used in the online world. The values have this many bits. So this is a very large, very, very, very large number needed to create this encryption scheme that I was just talking about. There's also this system called elliptic curve encryption, which is used a lot less often. But what you'll notice is that the numbers in size are much, much smaller. And elliptic curve cryptography relies on the same sort of idea of exponentiation being difficult. It's just changing the definition of what it means to multiply. So rather than saying multiplication is our traditional multiplication, what we're doing in elliptic curve cryptography is something like this. So this red line, curvy line here, is an elliptic curve. It has a formula looking like this. And anytime you draw a straight line passing through 2 of the points, you're guaranteed to hit a third. And that's because it's x to the third here. And so what we're gonna say is that p times q is going to equal, I'll pin out so I can draw, it's gonna equal this, I guess, like the negative of the third point. We do that sort of negation just so that the algebra works and everything's fine. But yeah, the sum or the product, I'll call it product in this sense, but usually we call it the sum. But the product of 2 points, we'll say, is the sort of the negative of the third point that the line will hit. And the reason I bring this up again is because this is just another algebra system we can use to do the same kind of public key cryptography that is done using RSA, but in slightly less information needing to be sent. So here's my nice little example of how you can figure out what form of encryption the website you're using has. So this is just a screenshot from Google Chrome. If you hit that little lock button in that top left corner and select the certificate, you're able to open up this box, which opens up in the General tab, but click on Details here. And you're able to scroll down and see that indeed Wikipedia uses elliptic curve cryptography, and you actually get to see how many bits are being used. So there are 256 bits. Let's get this out. 256 bits used in this elliptic curve cryptography to encrypt the Wikipedia page. This is just the home page, I guess. And similarly, if we do the same thing on the UWEC website, you'll find that the RSA encryption is being used. There's a RSA public key, and it has 2048 bits. So you might notice those bits are powers of 2. Yeah, anyway. So very large numbers in either case, but the RSA one is exceptionally larger. So that's kind of neat. And I like the fact that we can figure that out. Let me look at the time. So I'll say a little bit more before we get to the end, but thought I'd show you that cool way to figure out what you're doing on your own. So one last thing that I'll talk about is this idea of digital signatures, because you want to not only hide your information, but be able to prove that you are yourself. And there's not, say, a computer pretending to be you and maybe repeat your transaction or change your address without you knowing. Anything like that. So, let me. All right, cough a little bit. So a digital signature is a way that Alice or you can prove to Amazon or Bob that you are who you are. And what you do is you provide your own secret key. Oh, I know what I did. Never mind, ignore me. So what Alice is going to do is choose their own A, P, and K. So remember, K is the secret. A and P are going to be public, just like Bob did. And Alice will actually choose a random integer L. And between all of these numbers, M, L, M being the message, L being a random number, A, P, and K being choices, we're going to be able to generate a pair, R and S, that will contain sort of the information that Bob needs from Alice. There are formulas for these. I didn't feel like putting them up. I didn't feel like they were necessary for this talk, but they encode the secret information, and Alice is going to keep both L and K secret by sending R and S. So the importance of randomness here in choosing this L actually was shown sort of in 2012 with the PlayStation 3. They chose the same random L more than once just because their randomization algorithm wasn't so random. So in fact, hackers were able to get into the core software that is the PlayStation 3's I guess, foundational software, and were able to do kind of whatever the heck they wanted with it. So they were able to play whatever games they wanted, whether or not they were approved by Sony. So again, the importance here is the importance of the randomness in generating the values. So there's some more studies on sort of how to generate random numbers actually randomly. And that's what's actually used in our online communications. So we need to be able to be accurately random as we go. So let me see real quick. I'll point out there's this thing called dual ECDRBG, EC, elliptic curve, that generated random numbers. And what they found is that there's actually a very bad backdoor to this algorithm. So actually the random numbers created by this were causing problems. So this tool that felt very random, it was using curves to generate random numbers, could actually be manipulated, and you would be able to hack into the software, the messaging, if you knew something about the way that this was implemented. So actually the National Institute, what is this, of Science and Technology, withdrew this method of random number creation from its standards after learning about the backdoor. So one thing that's happening in cryptography research is sort of just breaking into the cryptography, into the algorithms, just to see whether or not it's actually safe. Yeah. So why don't I stop there and leave time for questions? Thank you for your attention.
Thank you, McKenzie. So as a reminder, folks can either drop their question into the chat box, or they can just unmute themselves and, ask the question. Oh, I think Jessica has a question.
Yeah, thank you. Thanks for the talk, McKenzie. You mostly answered the question that I had about random number generation there towards the end. So it sounds like NIST has a set of standards that should be met but in order to have like a good random number generator. Do you have like a link for that? Because it's something that I just don't have a lot of I don't have the computer science background to understand what makes a random number generator good. And I'd like to have a better vocabulary on that. So if you have any resources or thoughts on that.
Yes, I do have some readings. Let's see here. If I can. I mean, I don't think I have it on hand, but I can try and find where I have the link on some reading. Yeah, that's a good question.
Thank you.
I think it's Abra.
Hey, McKenzie. Can you talk a little bit about how this relates to your research?
Excellent question. Okay, how does this relate to my research? So what I like doing is taking polynomial equations and finding solutions to them. So the way that this specifically relates to my research comes up, oh, I did hit the right button, in this question of elliptic curve cryptography. So we need to be able to solve this equation in order to actually do this cryptography. So that is exactly where my research comes in.
Thank you.
Actually, McKenzie, if you don't mind, I have a follow-up question on Jessica's question. I know that you have additional resources that you can share, but is there kind of a brief description on what you would say to a layman? I'm not a mathematician, so how would you describe a good random number generator, or a good random number, to a layperson?
So the thing that was wrong with the elliptic curve random number generation was that if you knew the setup, you'd be able to predict the random number that came out. So a good random number generator would, I guess, maybe cloud or hide it a little bit better and sort of reduce the ability to predict the random number that's being generated.
Thank you. I think Alex has a question.
Yeah, McKenzie, I've always wondered if RSA is somehow a degenerate elliptic curve. I mean, RSA seems like a circle, and somehow I imagine the elliptic curve generating and it becomes RSA. Do you know if there's anything there? Or
Let's see. I haven't thought about that at all, but could you get RSA from elliptic curves? I can imagine that maybe that's possible. Sort of if you picked like a really boring elliptic curve, maybe you could get standard multiplication. But I don't know the answer to that.
Well, I'm sure you can take it offline as well. 'Cause you have more time for collegial discussions. Maybe that's elite. I'm actually looking at the time and being sensitive about the time. So thank you, McKenzie, for sharing your work with us. And thank you, everybody, for coming to this presentation. And hopefully you can join us again next week.
Thank you all.